15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello and thanks for joining us on another edition of the Space Nuts podcast, episode 223. My name is Andrew Dunkley, and joining me, as always, is the good Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
Hi, Andrew. It's nice to be good for a change.
Yeah. Oh, you're always good, Fred.
And some of the things that people used to say about me.
Oh, look, I think we've all been there.
Yeah.
They're saying it about the Federal Treasurer this week because the budget's been released, and it's the COVID budget. Some scary numbers, but you've got to keep the economy going, and that means spending money, and that means going into debt, and that means our children and our children's children and their children are all going to have to pick up the slack in a few years' time. But that's the way it goes, unfortunately, and I'm sure it'll be the same in many other countries around the world for years to come. Now, we've got a lot to talk about today. There's a few people you want to mention that have won prizes, the Nobel Prize we're talking about. One of the stories that's in the news this week that we're going to talk about is a study of comets, which has revealed that our solar system has a second alignment plane, which I think you'll find rather fascinating, but maybe more so, the possibility that around 24 odd exoplanets have better potential for life than Earth. That gets you thinking, doesn't it? So we'll look at that and some audience questions, one from Zoe in Northern Ireland and one from Gareth, coming up on this edition of Space Nuts. Now, Fred, a few people you want to mention briefly as recipients of the Nobel Prize. This would be the Nobel Prize for Science, is it?
It's physics, yeah. So the 2020 Nobel Prize for Physics, indeed, being shared in kind of two halves. Half goes to that esteemed British physicist, Sir Roger Penrose. You and I have talked about Roger many times because of his work on the idea that black holes might spawn new universes. But his prize is not for that. It's for the discovery that black hole formation is a robust prediction of the general theory of relativity. In other words, he basically proved that black holes exist mathematically. Very well-known physicist. I'm sure I've told you before, I was once at a public lecture that Roger gave here in Sydney, and halfway through the lecture his mobile phone rang and he took the call. So somebody in Oxford, I think, saying, "What do we do about this?" So he spoke for about 5 minutes and then got back to his lecture. Very, very individual style. So he's got half the prize, and the other half goes to two really big names in the science of black hole observations. Reinhard Genzel, who is German, and Andrea Gates, who is American. They have both independently and using different instruments have observed the orbits of stars around the black hole at the center of our galaxy, the supermassive black hole. So they've looked at the way stars swarm around it. They've measured the orbits of those stars, which is why we know the mass of that black hole so accurately. It's about 4 million times the mass of the sun. Andrea Gates has used the Keck telescopes in Hawaii to observe the galactic center, while Reinhard Genzel has used the European Southern Observatory's VLT, the Very Large Telescope down there in Chile. And they've produced movies over the last more than 20 years. They've both been working since the 1990s on this. They produced movies of the motion of these stars around the galactic center. It's stunning stuff. You can't actually see the galactic center directly in visible light, so they used infrared light to, the infrared radiation released by these stars to penetrate the dust that lies between ourselves and the galactic center. Fantastic stuff. I've been following their work for well over 20 years, and I'm delighted that they both shared the second half of this Nobel Prize, the first half going to Roger Penrose. So it's great news.
It is indeed, and I think anybody who achieves those sorts of levels of greatness certainly deserve to be recognised for it. And while the Nobel Prize came about because of something terribly destructive called dynamite, it's certainly being used for very good things these days, is it not?
Yeah, that's right. That's great stuff.
Yes, indeed. Now, let's move on to our first topic, and a study of comets revealing that our solar system has a second alignment plane. Now, I'm guessing the first one is the planets.
That's right, yeah, which is the plane of the orbit of the planets is called the ecliptic. It's a very flat plane. I mean, the misfits are Mercury and Venus near the middle. They're tilted at a few degrees to the plane, but most of the rest of the planets are essentially lie in this same plane. The plane of the Earth's orbit is actually the ecliptic itself. It was one of the reasons why Pluto was seen as an outsider very early on in the history of our knowledge of Pluto, because it's inclined at, if I remember rightly, it's 17 degrees, I think, to the ecliptic plane. So it sits well out of it. Anyway, that plane is what probably, 4.5 billion years ago, when the solar system was young, was a disk of material, the protoplanetary disk. But what's now happened is a scientist in Japan, whose name is Arika Higuchi, I think that's pronouncing it properly, who's actually at the University of Occupational and Environmental Health in Japan. It's an unusual name for a university, but she's working there, and basically has worked on some of the National Observatories projects, the National Observatory in Japan. So she's basically said, okay, that ecliptic plane may well have come about because of the influence of the gravity of our galaxy, the whole galaxy itself. In other words, the Milky Way, the plane of the Milky Way exerts gravitational forces. And so she looked at the way those forces, might have set up the ecliptic. In other words, the plane of this planetary disk, protoplanetary disk, in the early history of the solar system, how that might have been set up in the first place. Because the ecliptic's tilted over with respect to the disk of the Milky Way by about 60 degrees. It's an angle of roughly 60 degrees. And what she found was that there should be another plane that would be favoured by the effect of galactic gravity on the young solar system. So we've got the ecliptic tilted over at 60 degrees, and the calculations show that there should be another plane also at 60 degrees to the Milky Way, but in the opposite direction. And she called it the empty ecliptic because essentially it doesn't contain a planetary system like the real ecliptic. And that's a really interesting mathematical entity. It comes from her study of the gravitational pull of the galaxy. But then she looked at the orbits of comets, and that in itself is an interesting thing, because the suggestion is that comets actually started off being formed in the ecliptic. We now know that comets occupy this spherical shell around the solar system called the Oort cloud, and that's because they sort of come in from all directions. But what she's saying is that originally those comets would have been probably concentrated in the ecliptic, but also perhaps in what we now see as the empty ecliptic. And so, to cut a long story short, doing calculations of the orbits of comets, she looked at the statistics of it, and sure enough, she finds peaks in basically the direction of of the aphelion, the farthest point from the sun. She finds two peaks in this distribution in the comet, in our catalogue of comets, one near the ecliptic and one near the empty ecliptic. So it's really interesting to find that you can make a prediction from the dynamics of our own galaxy, how it relates to the solar system, and then make some look at the catalogue of cometary objects that we have already available and find that there is evidence that what she's saying is correct. A nice piece of work.
So would it be fair to say to this point in time we've just assumed that all the comets are on the same plane and we've not really looked into their origin to a greater degree because we weren't aware?
Yeah, so it's been the opposite. We've assumed that comets have come in from anywhere. They've been not in the plane, but in this spherical shell, the Oort cloud. And that's certainly the case. They do come in from all directions. That's why Jan Oort proposed the idea of this spherical shell of comets. But what this work is showing is that the Oort cloud probably started off exactly as you've said, with comets in the plane of the solar system, because that's sort of how they should be formed. But because comets are small objects and they're a long way out, they're in the depths of the solar system, they've been perturbed by the passage of other stars and things of that sort, which is why they're now in a spherical shell. But I think what she's saying is that even within that spherical distribution of comets, there is a sort of fossil remnant of the fact that they started off not only in the ecliptic, but also in this empty ecliptic as well, the two ecliptic directions. I haven't actually looked at the original paper for this, which I'm going to do because it's such interesting work. Basically, this is a second-hand report, but it's a very interesting piece of work, and it's quite far-reaching, really. It gives us an insight into the history of our solar system.
Yeah, and from what I've read, this now opens up future study of long-period comets so that they can, double-check their work, I suppose, so they can confirm their beliefs, confirm their theories. Yeah. And that's what happens, isn't it? When you come up with an idea, you've got to find a way of proving it.
Yeah, that's right. And actually, there's something on the agenda, which is, you and I have spoken about the Vera C. Rubin telescope, which used to be called the Large Synoptic Survey Telescope, should open for business. I think it's next year or the following year. It's been held up a bit by COVID-19. They're still building it down there in Chile. Not very far from La Serena. I saw it last year, actually, the construction site. But this telescope will survey the entire sky every week, effectively, every few days. And it's looking for what are called transient events. And that is, it'll pick up thousands of comets, this telescope, and as well as asteroids. So we might have more evidence for this empty ecliptic being a real thing by the time that those surveys are done on the Vera Rubin telescope.
Fascinating,
exciting stuff.
All right, well, it is, yes, and there'll definitely be more to talk about once that sort of information starts to filter back. So we will watch with interest, as I say, Fred. You are listening to the Space Nuts podcast. Andrew Dunkley here with Fred Watson over there.
Yes, I'm over here. He's over there.
Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity. Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Space Nuts.
Thanks for listening to the Space Nuts podcast. Andrew Dunkley here with the good Professor Fred Watson. Now, something I haven't mentioned for a long time is the Space Nuts shop. You can find it on our website, spacenutspodcast.com. You can click on the shop tab, and there's new products that I didn't even know we had, like the bubble-free stickers. You can now get the Space Nuts logo in the form of a sticker. There's the dad hat. What's a dad hat? I don't know what a dad hat is, but I'm thinking it's like a baseball cap, but a bit more daggy looking, perhaps. More akin to something an astronomer might wear. Whatever. Embroidered T-shirts for men and women. We've got the matte black magic coffee cup. We could probably drink tea out of it or something else. We've got polo shirts. We've got coloured mugs with the big logo on them. We've even got the unisex hoodie. The Space Nuts unisex hoodie is available. It's all on the Space Nuts shop on our website, spacenutspodcast.com. My goodness, it's just going gangbusters. And, there's some good stuff there. With Christmas coming up and, you've got a dad that doesn't have, you've got no idea what to get him, the dad hat would be a go, I reckon. Or a polo shirt or a mug, or get him one of everything. Why not? Now, Fred, let us move on to this study of, exoplanets, effectively. And what they've found is possibly a couple of dozen exoplanets that seem to have a better potential for life than Earth. Now, to this point in time, Earth is still the only place in the whole universe that we are aware of that has life. But we strongly suspect there will be other places, perhaps in our own solar system, that harbour some kind of life, probably microbial. But to actually be bold enough to step out and say, well, we think these 24-odd planets are probably better than Earth for harbouring life is a pretty big leap of faith, isn't it?
It's an interesting idea. Are there, places that can out-Earth the Earth? And apparently there are. This is some work.
We're making it easier for them.
Well, yes, that's right. It's, planets that may have conditions better than the Earth, and indeed may orbit stars that are better than our sun. So what has happened is a group of scientists led by somebody at Washington State University. I think he's also connected with the Technical University in Berlin. His name is Dirk Schulze-Markuch, and he has got together with some colleagues, René Heller from the Max Planck Institute for Solar System Research and Edouard Guinan of Villanova University. So there you are. This group of scientists have basically looked at what they call superhabitability criteria. So not just habitability, but superhabitability. And they've looked through the list of 4,500 now known exoplanets to find candidates for planets that might be better better than our own. And as you said, they found, I think it's 24, yes, within, none of them are within 100 light years, though. They're all quite a long way away. Nevertheless, so what they've done is taken these criteria. So first of all, of course, habitability doesn't mean that planets definitely have life. It means they've got the conditions that will be conducive to life. So super habitability means that they've got the conditions that will be super conducive to life. In other words, might be even better than they are here. So they looked at terrestrial type planets, rocky planets, orbiting basically in the Goldilocks zone of the Kepler Object of Interest exoplanet archive. This is, Kepler, the spacecraft that discovered a very large number of these exoplanets by the transit method. They pass in front of their parent stars and dim the light. So they've said, okay, just take the ones that live within the habitable zone, or the liquid water zone, the Goldilocks zone, as we call it, of these objects. And then what they also looked at was lifespan, how long a star lasts. So our sun has a lifespan roughly 10 billion years, and we're about halfway through it at the moment. But there are many other stars which are cooler and less massive, but go through their hydrogen fuel much more slowly. In particular, what we call K dwarf stars. They've got much, much longer lifespans, more than 20 billion years, sometimes up to 70 billion years. So it means that if you have a star that's going to last all this time, you're giving life a longer chance to evolve. You're to some extent improving the chances of life kicking off. On the other hand, you don't want a planet to be so old that it's got no geothermal heat, that its core is not liquid, because the liquid core is probably what generates a protective magnetic field, and you don't want to lose that. You don't want your magnetic field to wear out, so that you don't have protection from the radiation from your parent star, particularly because these K dwarfs are quite active and they probably spit out a lot more radiation than the sun does. So they make this point that the sweet spot for life is a planet that is between 5 billion and 8 billion years old. That's the kind of the zone that they think is the sweet spot. And then they talk about the size of a planet. Clearly, if you've got a planet that's bigger than the Earth, you might expect, unless it's an ocean world, that it would have more land. If it's a little bit bigger, they suggest 50% bigger than the Earth's mass, you'd retain more interior heat. And so you'd keep the magnetic field going, and you'd also have stronger gravity, a larger level of gravity, which means that you could keep an atmosphere, more solidly than a smaller planet. So they also point to a slightly warmer temperature. If I remember rightly, the Earth's average temperature, mean temperature, is 15 degrees Celsius. They suggest if you go up about 5 degrees, then, and especially if you've got more moisture in the atmosphere, you've got a better chance of life. And they point to the fact that this warmth and moisture preference we find on Earth, because when you look at tropical rainforests, you've got much greater biodiversity than you do elsewhere, in areas that are not as warm and moist. So those are the candidates, those are the criteria. They say that this 24 top planet candidates that they've dug out, none of them actually meet all their criteria, including the things that we've just listed. One of them has 4 of the critical characteristics, apparently, making it, as they say, possibly much more comfortable for life than our home planet. So Dirk Schulze-Markuch says, it's sometimes difficult to convey this principle of superhabitable planets because we think we have the best planet. We have a great number of complex and diverse life forms, and many that can survive in extreme environments. It's good to have adaptable life, but that doesn't mean we have the best of everything. So it's really quite an interesting idea, the idea of superhabitability. And, you know, when you do studies like this, Andrew, it essentially sheds a bit of more light on our own environment and tells us a little bit more about our own planet and, you know, what its shortcomings are in perhaps.
Yes. Yeah. Well, you know, I couldn't get past the headline "size matters," but obviously, if you could find a planet that's a little bit bigger, as you said, the gravity would work in our favour, keep the interior hotter for longer, and the atmosphere would hold better. But there's also the issue, if we ever are capable of leaving Earth and colonising another planet, we do have to actually find something that we can handle in terms of gravity. And that's something they never portray well in science fiction, because everyone can go from planet to planet in some circumstances and they all walk the same way regardless. But clearly there are huge challenges for any future exodus to a potentially livable planet outside of our own, and gravity's got to come into effect. It's we notice that when you get off the planet, muscle wastage. Well, the opposite would be true. If you went to a planet like Earth that was 1.5 times bigger, you would have issues with the amount of gravity, surely.
Yeah, it'd do your knees in for a start, I can tell you. Speaking as someone who's had his own knees done in by Earth's gravity, or one of them anyway. Look, just as a postscript to this, Andrew, as you probably know, I'm a big fan not of colonising other worlds, but of building our own megastructures that would allow us to live off Earth in space in large numbers with whatever gravity we choose, because these are like halo worlds where the gravity is artificially created by centrifugal force. So that's the way to do it. You can make your own gravity and you can go anywhere you like.
Now, that's good thinking. And that's probably the way migration will happen. Ultimately, you'll have generations of people moving through space.
Right. Yeah.
And the people who get there won't have been born for a long time after the exodus began. But one particular story I read recently, the name escapes me. The people of our solar system basically travelled in hollowed-out asteroids that had been turned into long-haul spaceships, and they were basically places where people lived, and they rotated, so there was gravity, and they had gardens. It was, it's not beyond the realms of possibility in the distant future. I'd suggest very clever thinking. I think it was a Kim Stanley Robinson novel. He's very clever. He's got a very, very sharp mind when it comes to potential ways of living in our solar system beyond Earth. It's he wrote that amazing Mars series too, which is a pretty heavy read, but fascinating bloke. Yeah, no, it's exciting that there are potentially livable planets out there. Hopefully, if they keep looking into it, we might find some that are a bit closer, which would may well be ideal for our future. Who knows? You're listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Space Nuts.
Now, something else I've not mentioned in recent episodes is that on our website you can subscribe to our mailing list. Now, you can do that through your favourite podcast distributor, whether that's iTunes or Apple or YouTube or Stitcher or Google or iHeartRadio, Spotify, or maybe through your standard RSS feed. They're all ways of subscribing, or you can simply subscribe by filling out the information on our mailing list, which you will find on our website, spacenutspodcast.com, and tap on the subscribe option. You can also become a patron by signing up to your via your favourite patron platform, whether it's Patreon, Acast, or Supercast. They're all available to you, and the packages are many and varied. Can cost you as little as $3 a month US, but if you want to put in more, it's totally up to you. And as I've said many times, it is optional. The good news is we will very, very soon have a bit more to add to our Patreon platforms in the form of bonus material. So stand by for that, not far away. Now, Fred, we've got some questions to tackle. And this one sort of caught us all by surprise in an amusing way because of I'm trying to, as I read it, think of the accent in my mind because I think it would just enhance it so beautifully. But even our producer, Hugh, was smiled when he read this one. This comes from Zoe in Northern Ireland. Hey, Zoe from Northern Ireland here. I rewatched the movie Interstellar the other day, and they show how some random planet orbiting a black hole, blah, blah, gravity makes time slower. In the movie, 1 hour on the planet is 7 years on Earth. And I was wondering if that fact or that actually can happen. If so, if you're able to watch Earth live from the planet, would Earth look like it was in fast forward? And this is the line that Hugh and I really love. Proper love the podcast, and you definitely make my long bus journeys to work much more enjoyable. Thank you. That's lovely, Zoe. Thank you for reaching out and asking that question. We've had people ask questions about Interstellar many times before, and I don't know if you've yet seen it, Fred.
Yes, I did. Yep.
Yes, yeah, and then so where they go down to that water planet that is orbiting a black hole, the issue becomes one of gravity, and as a consequence of that, the time dilation or variation causes an hour on the planet's surface to be a year. 7 years back on the spaceship and therefore Earth. And could that really happen?
So what this is depicting is something we call gravitational time dilation, the stretching of time by gravity. And we all experience it here on the surface of the Earth. Time's moving a little bit more slowly than it is for people up in the International Space Station because we're in the Earth's closer, to the centre of the Earth's gravitational field than they are. Not by much. I mean, the amount of dilation is tiny. But the idea of dilating time from 1 hour to 7 years it's not possible because that amount of time dilation would require such an enormous gravitational field that you would simply be spaghettified immediately. That's the issue, that your feet would feel a much greater gravitational pull than your head, so you get turned into spaghetti. That time dilation of 1 hour to 7 years has been decried many times by observers of this movie. Yes, the idea is correct that time is passing slower, in the gravitational field, but not by that amount. That amount is just a stretch too far by a very, very long way. So. No, not really. The fast forward effect, you would, in a sense, you'd see the Earth moving in fast forward if you could see it at all. Once again, it's for any kind of survivable environment, which is what's being depicted on the planet. The time dilation is much, much less. It's, something like 1 day becoming a microsecond longer or something like that. It's not 1 hour becoming 7 years.
So I suppose the question that pops into my mind is, what is a feasible limit on time dilation, gravitational dilation?
That you could survive.
Is there circumstances where it would be significant, I suppose?
I think the answer is no. If you wanted an environment that you could survive in, it wouldn't be significant.
Okay, so that takes us back to the.
That's off the top of my head, Andrew.
That takes us back to the discussion about discovering a livable exoplanet. Again, we talked about gravity in terms of the effect on the human body. Yeah. But you'd also have to take time into account, because you and I have talked before about trying to live on Mars, for example, which almost has the same amount of day and length as Earth, but long term it would be a very, very horrible place to try and live because your circadian rhythms wouldn't work, and they don't adjust well, as far as I remember our discussion. So there's all sorts of elements to take into account if we ever move. And
that's why we build our own space stations where you can make it 24-hour day.
Exactly.
To go back
to the point. But gravitational time dilation, not a thing to the extreme that they go to in that movie.
That's right.
But it is science fiction. It is science fiction, Zoe, and you can do anything in science fiction, as I've discovered, and and you can make it seem so very real. Look, it's a clever film. I love it. I really enjoy it. But they do stretch the creative license quite a bit in many aspects of the movie. But it wouldn't be science fiction if they didn't. So, yes. Now, and thanks for the question, Zoe, and thanks for telling us how much you enjoy the podcast. Now, let's move on to a question from Gareth Edwards. Gareth is referring back to a discussion we had some time ago, well, probably a month or so ago, about the rusty moon. We were talking about how the moon is actually rusting. He says, "Hi, I'm no chemist, as I'm sure this question reveals. In the recent episode about oxidization on the moon, you mentioned that there was no hydrogen on the moon, which came, there was hydrogen on the moon, which came from the ice in polar craters, but that there was no obvious local source of oxygen. But given that ice is H2O, why can't it also be the source of oxygen? Best regards, Gareth." I've got a feeling we might have actually said that at the time, or maybe we said it off camera. I'm not sure, but he brings up an interesting point.
I think what we said, Andrew, was, I wonder why you can't get ice, can't get the oxygen from H2O. So Gareth's question's a great one, and I'm pretty sure we discussed it. I think it was offline that we ourselves didn't understand. And I think the answer is to do with, it's to do with the chemistry. And I'm not a chemist either, Gareth, so you and I are in the same boat here. But it's certainly true that the lunar soil, the natural lunar soil, has a huge component of oxygen in it. A lot of the minerals are oxides of one form or another. And there's some work that's to do with the Artemis project that is going to the moon now. People looking long term about whether you can actually use the lunar soil to generate oxygen. And apparently, one of the minerals that is very rich in oxygen is something called ilmenite, which again is a bit like what we're talking about. We were talking about hematite, which is iron and oxygen. Ilmenite is a mixture of iron, titanium, and oxygen. And so, the Artemis project talks about the chemistry required to extract that. So I'm not sure what the answer to your question is, but I think it is to do with the way the oxygen is bound up in these different minerals. And it may well be that the hydrogen is the hydrogen, that is present in the water of the poles, that tends to leak away, so that you would expect you'd end up with an oxygen-rich environment in those frozen puddles in the south and north poles of the moon. Why doesn't that provide the oxygen needed to oxidize iron to make hematite? And I don't know the answer to that. Some subtle chemistry here. If I get time in the next week or so, I'll go back to the original paper, which talked about the rusting of the moon, and try and find out a bit more detail. But I'm sorry I don't have the answer at the moment. But it's a really good question. And if there's anybody out there who knows the answer, don't hesitate to let us know.
Absolutely, yes. We do love to hear from you. And sometimes people have put forward comments that are sort of, we go, oh, yes, of course, that would make sense.
That's the answer. Yes.
We welcome that, as we do welcome your questions, of course, via our website, spacenutspodcast.com. You can just message us your question the traditional way via text, or you can record your question on the AMA link on our website. Just click on that. If you've got a device with a microphone built in, like a smartphone or a tablet or a laptop computer or whatever they call them these days, notebook, you can just click record and say, "Hi, I'm Fred from Sydney and I want to know what Andrew's next novel is about." And we'll spend 24 hours talking about it for you. No questions asked. But, ask us anything you like and I will hand all that over to Fred because I don't have to answer any of them, which is a blessing. Yes, we do appreciate your questions and your feedback. Sometimes we just get emails from people wanting to say hi, and that's fine too. And, I've found a long-suffering Cincinnati Bengals fan, which I mentioned the other day. They actually achieved a draw, their first non-loss of the season the other day, which I was impressed with. What a dogged battle that game was. But that's beside the point. I think we've reached the end of another program. Fred, thank you so much.
Oh, it's a pleasure, Andrew. That took me by surprise. I thought we had hours to go yet.
Probably. Well, we've gone a bit quicker this week than we normally would.
Yeah, very good.
I take the philosophy that a story should be as long as it takes to tell. Exactly. So there we have it.
Especially when you don't know the answer.
But I will say that if you are a patron through Patreon or Supercast, some bonus material coming your way very, very soon. So stand by for that. We'll be getting onto that very, very quickly indeed. So, Fred, thank you very much. We'll catch you again next week.
Sounds great, Andrew. Thanks a lot. Take care. Look after yourself. See you soon.
You too. That's Fred Watson, Astronomer-at-Large, part of the crew here on the good ship Space Nuts. And from me, Andrew Dunkley, have a good week, stay safe, and we'll catch you again real soon.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.